My project focuses on predicting satellite drag in low Earth orbit during geomagnetic storms. These storms cause atmospheric changes that increase drag, reducing satellite lifespan and reliability. I aim to show how machine learning can improve predictions and support operators with proactive actions, leading to better satellite resource management and operational planning. Geomagnetic storms cause density changes and upwelling in the upper atmosphere, creating unpredictable drag forces on LEO satellites. Traditional models can't capture this complexity, leading to mission risks and shortened lifespans. By analyzing solar activity effects and Joule heating processes, I highlight the need for more advanced predictive solutions that adapt to varying conditions. The demand for accurate satellite drag prediction is growing rapidly. With thousands of LEO satellites planned by companies like SpaceX, Amazon, and OneWeb, reliable forecasting directly impacts lifespan and safety. Space agencies and space weather forecasters also rely on improved tools to protect investments and ensure resilience in critical communication and navigation infrastructure. I see machine learning as ideal for this domain because it handles complex, nonlinear relationships in large datasets. With rich data from solar activity, geomagnetics, and satellite observations, ML techniques allow adaptive modeling, identify feature importance, and improve accuracy beyond classical models. This makes ML highly suited for predicting dynamic space weather effects. My target users are commercial LEO satellite operators who need better lifetime management solutions. Right now, drag prediction relies on empirical models with limited accuracy, creating resource inefficiencies. Closing this gap is essential. With precise ML-based prediction models, I aim to improve forecasts and optimize satellite operations effectively. For me, success means extending satellite mission lifespans through improved prediction accuracy. The expected impact includes operational efficiency gains and better use of computational resources. Key metrics are satellite drag forecast accuracy, adaptability across geomagnetic conditions, and overall reliability. Achieving these goals will validate the system's value and ensure strong business impact. I identified several factors that influence satellite drag and prediction success. These include solar activity, geomagnetic fluctuations, and atmospheric responses. Domain expertise from operators, scientists, and ground observatories is also vital. Considering both environmental inputs and satellite-specific parameters ensures my machine learning predictions remain robust and practically useful for operations. My validation plan focuses on input-output consistency and data diversity. I use solar and geomagnetic indices, model them with ML approaches, and iterate experiments for adaptability. Prediction accuracy is benchmarked under storm and quiet conditions. With iterative refinements, I ensure that drag forecasting is robust, reliable, and scalable for real-world operations. I prefer a cloud-based ML architecture because of its strong computational power, ability to process vast historical and real-time datasets, and easy collaboration. Edge systems are limited by onboard resources, making them unsuitable for advanced models. Cloud deployment ensures accessibility, scalability, and adaptability, meeting the needs of operators and forecasters. I propose offline learning with periodic updates. Using historical datasets gives stability, robustness, and thorough validation in a high-stake domain. While online learning could adapt faster, offline learning balances reliability with safety. Regular updates allow me to keep the model accurate without compromising trust in operational environments. I favor online predictions because batch methods are too rigid for the dynamic conditions caused by the geomagnetic storms. Online predictions provide real-time responses that help operators make timely decisions. This is critical when track changes rapidly. Immediate access to forecasts ensures more resilient and responsive satellite operations during storm events. Key risk I see is training serving skill. The difference between model training and real input data cause mismatches. Problems include pre-processing inconsistencies, feature mismatch, or synthetic data reliance. I plan to mitigate this with standardized pipelines, robust validation, and continuous monitoring to ensure real-world consistency. Latency is another risk I must address, since real-world requirements can strain infrastructure. Complex models and data integration can introduce delays, reducing forecast usefulness during storms. My solution is to optimize infrastructure and balance model complexity so predictions remain both fast and accurate. I also need to tackle data drift. Solar activity, atmospheric changes, and sensor updates constantly shift input distributions, which degrades accuracy if unchecked. I plan continuous monitoring, retraining strategies, and adaptive algorithm to maintain prediction quality and reliability. Concept drift is another challenge. Storm dynamics, new satellite designs, or unforeseen events can invalidate existing models. I will counter this with adaptive learning, domain expertise, and fallback strategies that predictions stay relevant despite long-term changes. Finally, I must consider risks like model overfitting, interpretability issues, and integration challenges. Overfitting reduces reliability, while interpretability affects operators' trust, and integration can be complex across stakeholders. By using explainable ML, rigorous testing, and streamlined pipelines, I can ensure the system remains transparent, scalable, and widely applicable.